Hello, this is the first in a series of screencasts on the subject of redox chemistry for the module CHE10063. Okay, so today what we're going to do is going to start redox chemistry and we're going to talk about oxidation states because, as I said in this sort of introduction to redox chemistry, we need to be able to determine what the oxidation state is because in redox chemistry, one of the species' oxidation state is going to increase, whereas the other one is going to decrease in order for a reduction and an oxidation to have occurred, which is required for a redox reaction. Okay, so yeah, first thing we're going to do is look at how we actually identify the formal oxidation states, and this is actually noted about sort of kind of throughout inorganic chemistry. There's quite a few sections that talk about oxidation states, and I will link to a couple of them in these slides. But the first place where it's mentioned in inorganic chemistry in the textbook is page 57, and this QR code here links directly to that page. Okay, so what I wanted to do in order to start talking about oxidation states and to introduce the concept of oxidation states was to talk about this specific compound, which is called tetraethyl lead. Now, this predates you considerably, but this is basically what can be only described as sort of clever, with hyphenated commas, chemistry in the 20th century, so in the 1900s. Basically, old cars used to have issues with uncontrolled combustion, which is also known as knocking, and this species here, tetraethyl lead, was introduced because it suppressed that and meant that the cars would run further, and that it would mean that the petrol was basically more effective. Okay, so we used to have effectively leaded petrol, and so if you ever wondered why petrol is described as unleaded, or can be sometimes described as unleaded, then that's because it doesn't have this stuff in it, and this is why. So okay, and basically what happened is when we put this into the engine, obviously it controlled the knocking, which was great, big plus for chemistry at the time. But these following reactions actually took place in the engine. Okay, so you had this species reacting with some oxygen to give us sort of things that are not too bad, so carbon dioxide and water, but also giving us straight, lead metal. Okay, and equally within the engine, because there's plenty of oxygen kicking around in the engine, that lead could react to give us lead oxide. Okay. And basically this led to the buildups of both of these materials in the engine, which basically ruined it. Okay, I mean, because if you're going to get lead buildup or lead oxide buildup, it's just going to get in the way of the moving parts, and that's what fouled means basically. So in order to prevent that, of course, chemistry came along again and said, hey, we've got a solution to this, and they used 1,2-dibromoethane. Okay, so that probably worked, but the problem with that is that then reacted with those lead species to form lead bromides, and these are volatile, and that's all very well, provided that they don't get made at massive amounts, and maybe they go straight into some sort of waste material area. But the problem here is that these were being spat out the exhausts of the car. Now, in anyone that contacted with these lead bromides, that could lead to lead poisoning, but this was particularly bad for children, and that's because children are shorter and therefore much closer to the car exhausts than adults would be. So this was a big problem, and this is why we now have unleaded petrol. Okay. The key point when it comes to oxidation states, of course, it's a nice story, of course, of chemistry not quite getting it right, but the key point within those reactions are that these are actually redox reactions. So, in tetraethyl lead, you have lead in the oxidation state +4, whereas, in just the element lead, its oxidation state is 0, and in lead oxide it is 2+, and these are the formal oxidation states of lead in these cases. Okay, and obviously what I've said already is that we need to know how to assign formal oxidation states. Okay, and this is how we do it. Okay, so rule number 1 is that an element, so in this case lead, or same thing could be applied to oxygen, as in O2, that we saw in a previous reaction too, that has an oxidation state always equal to 0, i.e. it's not charged. That shouldn't be surprising to you because, an atom isn't charged, right? Okay, so, that makes sense. The next rule, fluorine. If fluorine's in a compound, it is always going to be in oxidation state -1, and that's just simply because of the electronegativity of fluorine. Okay. Likewise, oxidation in a compound, unless it's combined with fluorine, in which point in time it makes a molecule called FOOF, which is just as dangerous as it sounds. But that species is always, oxygen is always otherwise in an oxidation state -2, which incidentally is why lead oxide, lead is in the oxidation state of 2+. Okay, and that brings us, to the next one, which is that alkaline metal cations, which are kind of a bit like the opposite of fluorine, aren't they? They will always be quite happy to lose an electron, and are really ready to do that. And so their oxidation state is almost always +1 in a compound, or it is always +1. It's not going to be anything more than that, is it? And the final point, which is why lead has a 2+ here, is that if you have a neutral species like lead oxide, then the sum of the oxidation states, so oxygen's in 2-, lead's in 2+, the sum of 2+ plus 2- is 0. That sum has to be equal to 0 if it's a neutral species, but obviously if it's a charged species, the sum of oxidation states within that species has to be equal to its total charge. Okay? And there are a couple of other resources down here that I've linked to that you might go and see if you want a bit more information on how to do this. But these rules are also included on the page that I've already linked to you, page 57 that I had right at the beginning, that QR code on the first slide. So let's just talk a little bit about periodic trends in oxidation states. Now, this will overlap a little bit with some of the periodic trends material you have later in this semester, but and maybe next semester. But nevertheless, it's worth doing. So, as you might expect, some of these oxidation states are not going to be particularly surprising to you. So, for example, oxygen we've already said is -2, and fluorine's -1, so that's pretty straightforward. And all of the noble gases tend to have an oxidation state of 0. Okay, now some of the later ones can form other oxidation states, but generally speaking their most stable state is 0. Okay, so down this line here, these are our halogens, aren't they? And these tend to have an oxidation state of -1, and that's just because of their electronegativity and their preference to just gain 1 electron in order to form a complete shell. Okay, and likewise, group 16, you can see -2 becoming pretty popular. Yeah. Typically speaking, groups 1, 2 that are not shown here, but 13 and 14 would tend to lose electrons, and they would tend to have, oxidation states that are positive, therefore, because they've lost electrons. Okay. Yeah. Basically, and sort of the ones in the middle are somewhat in the middle with a bit of a combination. So nitrogen will happily pick up 3 electrons, but equally it can lose them. And we'll see an example where it does both at the end of here when I go through a model example of how to assign oxidation states. Okay. Now just note in this table I've ringed the noble gas configurations. Obviously I should have also ringed -3 for nitrogen and for phosphorus, because that also gives us noble gas configurations. But yeah, you can see they're all ringed here. And so these do the bold ones do tend to be the ones that give you the noble gas configuration, and the bold are the most common versions. Okay. Interestingly, when you get down the group, you might have noticed that these +4. So, for example, for group 14, the +4 state is often the most common one, because that's the one that gives you the noble gas configuration. But as you go down the group, it stops becoming so common, and particularly for lead, +2 is more common than +4, and that's obviously not a noble gas configuration. Okay. And the reason for this is basically something known as the inert pair effect. This can be explained in a number of different ways, but one of the best ways that's currently thought is this sort of idea of a large quantity of energy is required to remove those s2 electrons after you've kind of removed the p electrons. So the configuration of lead 0 would be s2 P2, wouldn't it? So you're going to lose 2 p electrons to get to the +2 state, and then you might lose another 2 electrons to get to that noble gas configuration. But that removal of those s electrons is harder, and you're going to see why that might be when Dave introduced the concept of atomic orbitals to you. Again, this topic is covered in some detail on page 297 of Inorganic Chemistry. So just to sort of finish this in terms of the periodic trends of these things, debug elements. This is where you get a lot of different oxidation states, and you're going to learn about that in greater depth sort of later this semester next year. Okay, but for example, the common classics are magnesium and chromium, manganese, sorry, and chromium, that give you multiple oxidation states, and you'll see that there's many stable species within this manganese line. For example, again, you have the bold ones, which are the most common, but nevertheless, some of the others are pretty common too. And again, this is covered on page 298 of Inorganic Chemistry. Okay, so as a final exercise, I just wanted to go through a worked example of how we might assign formal oxidation states to the atoms in these following compounds, okay? And the way we've got to do this is by exaggerating the ionic character of each of the bonds, okay? So, obviously, in particular, the molecule under A is clearly covalently bonded. But each of these bonds would be somehow, ionic in some character of that is going to be ionic. So there'll be a delta negative of the fluorine and a delta to positive on the nitrogen here. And likewise here, there'll be a delta negative on the nitrogen, and here there'll be a delta positive on the hydrogen. Again, due to, polarizability and electronegativity. Okay, so this is the sort of ionic character, and we're exaggerating it until we have a full ionic bond, and that's how we're going to get our oxidation states. So we also need to obey the rules. So the rules state that F is always -1. So the oxidation state of F is always -1. Okay, so that's -1, -1. Now the next thing we can say is that N is more electronegative than hydrogen. So we can say, therefore, on that basis that the hydrogen is going to have a +1 charge. And then N we need to come back to in a second. The final thing we can say is that N has common oxidation states of -3 and +3, particularly -3 because that leads to a noble gas configuration, right? And so, if this is delta plus, this is going to have more likely to be +3, and this is more likely to be -3. Okay, now of course, in order to this is fine because this all adds up to 0, which is a neutral molecule, so that's fine. And of course you might spot that, well, I could have given the nitrogens each oxidation states of 0, or I could have given them each oxidation states of -1 and +1, and you still would have had a number that added up to 0. Now that's fine, but it doesn't really take into account the data we've got in front of us. Okay, so let's move on to this second one, and before I do that, I just need to make a slight amendment to this, which is that this should be K2Cr2O7, okay, because otherwise it doesn't work, so apologies for that mistake. Okay, but anyway, K, or potassium, that's an alkali metal, so that has an oxidation state of +1, so that's basically +1. Now, oxygen is going to be -2, and of course there are 7 oxygens, so it's 7 times -2 is the total charge because of that, which is -14. Now there's 2 of those, so that gives us +2. So therefore, sort of to make the whole molecule add up to a neutral charge, then the chromiums have to be, essentially the difference, basically 12 over 2, which is equal to +6. Okay, so this is going to be +6, and this is the old hexavalent chromium that is popular in a certain movie. Okay, and this indeed is actually a very, very strong oxidant because chromium has a very great tendency to want to reduce that oxidation state. Okay, so that's just the way we can assign formal oxidation states to the atoms. I will include some more examples for you to practice in the quiz. But with that, let's move on and talk about redox chemistry in a bit more detail in the next screencast.